Hey everyone, I'm Anirudh, roll number 21 CS10004 from section 8, a member of team 10, FINISTE ACADMICOS.
Hello everyone, this is Iit Kgp and my roll number is 21 MA10059 and I am from team 10, FINISTE ACADMICOS.
Myself Ketan Agarwal, roll number 21 AG10019 from team 10.
Hello everyone, my name is Iit Singh and my roll number is 21CS10044. I am from team 10.
Hello everyone, my name is Sahil Kumar Singh and my roll number is 21 ME10066. I'm from section 8 and I'm a team member of team 10.
We have made an AR headset as our project. So before getting into the technical details, let me give you a brief introduction. Reality headset is a specialized head-mounted device that provides a simulated visual and auditory environment. It provides virtual images, videos, animations, or informational content to the user. They are programmed to change to display info as commanded by the user on the go and are able to change their optical properties at runtime. They can serve as a fully fledged GPS navigation system, displaying maps and current coordinates. They can be remotely controlled by the phone and alert the user to communicate data such as calls, SMS, emails, and calendar invites. So now let's talk about the components used in our project. The major components are first Arduino Uno R3 SMT board, which is the microcontroller board containing 14 digital input-output pins and 6 analog input pins, a 16 MHz ceramic resonator, a USB connection, a power jack and an ICSP header and a reset button, a 1.3-inch OLED display module 4-pin with a 128x64 resolution, speaker and its part for the audio output, a 6V 180 mAh solar panel which will receive the signal transmitted by the light source, a laser module to send the signal to the solar panel, a 9V battery and an audio jack. In our headset, we are transmitting the data through Li-Fi. So now let's first understand what is Li-Fi. Li-Fi is a wireless communication technology that utilizes light to transmit data at high speeds over visible, UV and infrared spectrum. The key technical difference between Li-Fi and Wi-Fi is that Wi-Fi uses radio frequency to induce a voltage in an antenna to transmit data, whereas Li-Fi uses the modulation of light intensity to transmit data. The visible light spectrum is 10,000 times larger than the entire radio frequency spectrum. Researchers have reached data rates of over 224 gigabits per second using Li-Fi. Li-Fi is considered to be 10 times cheaper than Wi-Fi. Now let's understand the working of the OLED. An organic light emitting diode is a LED in which the emissive electroluminescent layer is a film of organic compound that emits light in response to an electric current. It is the bilayer screen having the emissive and the conductive layer between the cathode and the anode. To make a OLED light up, we introduce a potential difference between the anode and the cathode, and as the electricity starts to flow, the cathode receives electron and the anode loses electron, or we can say the anode gains holes. As a result, the emissive layer becomes negatively charged and the conductive layer becomes positively charged. Positive holes have more mobility than the electrons, and hence they jump from the conductive layer to the emissive layer. When a hole meets an electron, the two things cancel out and release a brief burst of energy in the form of a particle of light, that is a photon. And because this happens many times a second, the OLED produces continuous light as long as the current keeps flowing. Now let's understand inter-integrated circuits or I2C communication. It is the communication protocol for the transfer of data between a central processor and multiple integrated circuits on the same circuit board using just two common wires. Data bits are transferred one by one at regular intervals of time set by a reference clock line. Only two common bus lines are required to control any device on the I2C network. The data transfer speed can be adjusted whenever required. New devices can simply be connected to the two common I2C bus lines. The two I2C bus lines are serial data line and serial clock line. The data to be transferred is sent through the serial data line and is synchronized with the clock signal from the serial clock line. All the devices are connected to the same serial data line and serial clock line. Now let's go through the soul of our project, that is the code part.
This project that we have done can be totally divided into three subcategories: the test code, the companion code, and the actual input-output program. To give a brief overview of each of these, the test code contains the piece of code that we run to check whether the devices are in working condition. That is, whether the Arduino board, the solar panels, and the OLED screen, whether they all are in working condition, and whether they receive and transmit information or not. The companion app code is the code that is required to parse information from the input device. Here it would be the cell phone. And the actual input output code would be the code that would decode this information that is parsed from the companion code and sent through light as light pulses. To talk more in detail, let us see the test code first. As the name suggests, it contains all blocks of code that is needed to test whether all devices are in working condition. The first test would be the test for the Arduino board itself, where we set the built-in LED pin, that is in pin 13, as high for a second, and then we set it to low for another second, that we make the LED light blink. If it blinks, it means the Arduino is in working condition and it is receiving and transmitting information. The second test would be the address test, wherein as we are using an OLED display with an I2C communication protocol, we need an I2C address for the display screen, which is unique to each device. So we use a scanner to get the address for the OLED screen that we are using, and for this we give a wire.begin transmission, which is basically it transmits the address code in itself to the Arduino, so that it can be stored in the form of a string. And we also get an error when we end transmission. If the error is 0, that means there is no error and an address has been found, and we print the address. But if the error is 4, then we get an unknown address, that is basically an address that is either corrupt, or it is an address that is higher than the 7-bit standard address. Since after this we also give a 0 device error, which means that there is no I2C device found, which is another case, and we loop it over after 5 seconds, so that we need not plug it out and plug it back in for finding out different devices. The third part of the test code would be the test for the OLED screen itself, where we define all different libraries that we are going to be using, including the Adafruit JFX and the SST1306 modules, which are needed for printing the text on the display. What we do is we define the display with a screen width, screen height, that is 128x64 that we are using here, and a reset pin of -1, which is a standard for any I2C communication because there is no reset pin involved. And the I2C protocol itself works as a reset pin. And we begin the serial at a baud rate of 9600, and when there is no OLED screen connected, we print in that the allocation has been failed, and we wait for an OLED screen to be connected. And when it is connected, we clear the display, because after connection there would be an Adafruit logo that is being displayed, because that is the imported module GFX. And we clear the display. We set the text size to 1 pixel, we set the text color to white, and we set the cursor at 010 so that it prints at 010, and we give the command to print hello world, and the screen prints hello world, and then we give display so that the printed thing can be seen. Finally, we come to the last test, that is the test for the input from the solar panel, where we send a piece of a character or some signal through the phone or through the input, and then we check whether the solar panel is receiving and communicating it. So basically what we're going to do is we are going to send 1 or 0 through the phone input, and then we are going to check whether this 1 or 0 would be recognized by the Arduino. For that, we define the built-in LED at pin 13, and then we set it at output mode, which is actually not necessary, but we have done it for readability. And then we get data basically if it's 1 or 0, and then when a signal is transmitted, the serial.available would be true. There would be a character in buffer, and then we'd read that character, and then we'd make it concatenated data. And then if data is 1, we'd make the built-in LED to light up, and if it's 0, we make the built-in LED become low. And if it lights up, that means that the solar panel is transmitting and everything is all right. Next comes the companion code, which is the APK file that is built to transmit and parse the needed data. What it does is that it makes a string of date, bar time, bar text, bar phone, and it carries it through and it sends it for transmission. Basically, it encodes it as ones and zeros, and basically there is an encoding procedure taking place. And this signal would be sent for transmission through light. A point to note is that there is a Bluetooth client involved here in the code, which is an inbuilt variable, and it's not actually connected to Bluetooth in any way, but it is a useful variable to involve communication protocols, because it has a lot of built-in functionalities like connect and disconnect, which would enable us to be flexible in what we do. And we can see that there is a lot of things involved with the command string, and when is phone is true, we get the phone number and all that, and when is text is true, we get the text to be displayed, and this all happens when Bluetooth client is connected. In this project, when the Bluetooth client is connected, it means that the transmitting circuit is actually connected to the phone, and when it is not connected, it means that the transmitting device is either not connected or we have forcefully disconnected it. And so when it is connected, we give the phone notifications, we give the text notifications if there are any, and this would be transmitted in the form of a string of date, bar time, bar phone, bar text. And finally, when we run an audio app in the background, the audio signal would be enveloping all these 4 signals. So basically, the final decoded output would look like date, bar time, bar phone, bar text, bar audio. It would be in the form of a string, but and that's what we found by experimenting. The last piece of code that we're going to be looking at is the actual input-output code, which is going to be the main body of the code, and this is what is going to be uploaded to the Arduino. It is designed to parse through the encoded string and decode it to display it as text and all that. And without going into actual line-by-line explanation, I'd be giving just the highlights of the code. We define the OLED reset pin as -1, we define the height as 64, we define the width as 128, as we're working with a 128 x 64 pixel screen. We include SPI, we include wire, we include Adafruit GFX and the SSD 1306 modules, and we define the display as shown. We define 5 strings: date, time, phone, text, and audio, and the audio string is for convenience and not for anything else. We again begin at 9600 bauds. We set A0 pin as an output pin. We begin the OLED screen at address 0x3c. We display the Adafruit logo. We make it stay for 2 seconds and we clear it. And then we check the serial buffer whether characters have been received or not. That is whether the solar panel is receiving light inputs. So when the characters are available in the buffer, we read the strings, and since we are separating it by bars, we read until each bar. The date would be until the first bar, the time would be until the second bar, the phone would be until the third bar, the text would be until the fourth bar, and the audio would be the last. And finally, if there is no text or phone inputs, they default to values such as a small text and small phone. So if they are the default values, we make cases such that we do not lose information or we do not lose connection. So basically, if text and phone both assume the default values, we print in the date and time. If text is not default but the phone is the default value, we print in the text message that is received. We make it stay for 5 seconds and we clear it. And if the text is the default but the phone is not the default value, we print in the phone number that is being displayed, who is calling us. We delay it for 5 seconds and we clear it. And lastly, you can see that I have written an if odd and then analog write a not odd. That is just for convenience sake, because that is actually a redundant piece of code, but without that the code actually starts to fail, because the audio string that has to be written at a not, it seems. But connecting the solar panels directly to the earphones, the speaker modules also, that works, because it seems that it can discard all the other pieces of text that are being encoded without disturbing the audio signal. It basically it accepts the audio signal and discards the rest. And that's it. Thank you.
If code is the soul of our project, then this is no less than the body. So now let's go through the physical demonstration of our headset.
For the AR headset, we'll be using Arduino board, OLED screen, solar panel, earphones which are soldered to the solar panel, the battery to power up the Arduino, the phone which is connected to the laser. The phone has a companion app in it which will help us to transfer data from the phone to the Arduino using the laser connected to it. We'll be putting the Arduino OLED screen, solar panel, battery inside the helmet, and we'll be using the phone to transfer the data to the Arduino. So here we can see that all the hardware components have been put inside this helmet, and here the OLED screen, that is this screen, is visible in front of our right eye. So here's the solar panel at the left side of the helmet, and since there is no laser pointing the solar panel, the screen reads no data. So now we'll try pointing the laser to the solar panel. As you can see, we have put the input, that is the laser light, has been pointed towards the solar panel. Here it is visible, and as soon as the laser hits the solar panel, our screen reads the data and shows us the time and the date, which is 1:15 AM and 25th Feb 2022. The AR headset has more aspect to it, that is, it also notifies us with the phone number if we get a call to the phone which is connected to this AR headset. As I am calling, it shows my number. Here's the number and also the status. After 10 seconds, it tells us if what's the status of the call. Like here it says call not attended. The last but not the least thing the OLED screen and this AR headset can do is it can also show the text message that we have got from the to the phone that is connected to this AR headset through the Li-Fi. So I have just texted hey how are you to the phone which is connected to it, and it displays on this OLED screen. Here the earphones connected to the AR headset through the solar panel can also be used to listen to music. So let's try this as well. I will play some music in the phone which is connected to the AR headset, and it should work. Let's try this. I think the music is quite audible. So that's our project. Thank you.
This was our project AR headset we made using Arduino and Li-Fi. We have shown you some basic functionalities using our working prototype, and it can be further improved. So with this, I would like to conclude it. So thank you.